was an important factor in selecting the melt refining process for the EBR2 fuel cycle. The mold containing an ingot of purified alloy is transferred to a sampling station. The as-cast ingot contains two protrusions on the bottom which are sheared off to provide the samples required for analysis. On the basis of these analyses and the weight of the ingot, the required amount of additional enrichment and alloying is calculated. Fuel processing completed, the purified ingot is transferred to fuel fabrication, the second phase of the fuel cycle. The primary aspect of the second phase is the development of the injection casting technique. While prototype equipment is being fabricated, development work proceeds in conventional furnaces. The molds used are graphite-coated, precision-bore Vicor tubes. A cluster of these tubes is suspended above the melting crucible. The ingot is vacuum melted and the tubes plunged into the molten alloy. At the same time, the furnace is pressurized and molten metal is forced up into the molds. Dimensional variations of the cast pins are essentially the same as those of the Vicor tubing. Removal of the precision bore tubing is accomplished by crushing. The finished fuel pin is brushed to remove residual glass and requires no further machining. The pins in a carrier magazine are transferred to the final phase of the fuel cycle, the reassembly. The initial step, performed in a glove box external to the shielded area, is the charging of an exact amount of sodium to each rib stainless steel fuel can. The purpose of this sodium is to fill the 6 mil annulus which will exist between the fuel pin and fuel can. This provides a good heat transfer path and also permits unrestricted thermal expansion and contraction. Placed in a carrier basket and introduced to the process cell, the sodium-filled cans are ready for pin loading. Matching of the fuel pin carrier magazine and carrier basket operates a trip mechanism introducing the fuel pins into the sodium-charged tubes. The carrier basket containing the assembled fuel elements is placed on a heated syntron vibrator, which melts the sodium and settles the fuel pins to the bottom of the element tube. Final operation of fuel element assembly is the introduction of the restrainer cap and closure by automatic welding. The completed element is leak tested and bond tested before being returned to the sub-assembly. Fuel elements are next assembled with blanket sections fabricated independently of this operation. The fuel elements are threaded onto a location grid. Requirements of accurate sized cooling channels, limited mechanical motion, and normal dimensional tolerances restrict the assembly to a specific pattern. Clustering of the fuel elements limits heat dissipation by natural convection, and assembling must be done in a cooling jacket. During loading procedure, a programmer maintains a record of the last element loaded and indicates the next one to be loaded. 91 fuel elements complete the sub-assembly and are encased in a hex shroud. This sub-assembly is a completed product of the integrated fuel cycle as developed for EBR2. Operation of EBR1 demonstrated the breeding concept and reaffirmed the importance of fast reactors for complete utilization of our uranium resources. EBR1 measurements, augmented by other experimental data, have established that a breeding ratio of 1 2/10 can be achieved in a practical uranium-235 fueled power plant, and at least 1 5/10 with plutonium fuel. Successful operation of 3 full-size sodium pumps each of them the largest of their type yet produced, lends assurance that practical sodium coolant systems can be developed for large reactors. The inclusion of an integrated fuel cycle will permit a true evaluation of the economic feasibility of the fast reactor concept. This has been a report of Argonne National Laboratory's continuing research and development program required to support a reactor concept. The ultimate aim of such a program is to establish the feasibility of large-scale fast power breeder reactors.